Good afternoon, everyone. Welcome to the last session of BSides San Francisco 2018. I'm honored to be here in front of you, and it's a pretty exciting talk. First of all, theater setting, pretty awesome settings, huh? The lounge chairs, pretty good. I presented at BSides, this will be my third or fourth presentation. Some of you may have seen previous ones. But they've all been non-technical, non-security talks. My first technical security talk. My version of imposter syndrome is I never know enough and I'm always behind. You may see evidence of both of those today, and I'm fine with that. There may be people here who are much more expert on many of the topics I touch on today. And if you want to bring that up in the Q&A, I'm fine with that. I just want to put that out there that I'm here in front of you with my first technical talk that I didn't think was technical enough to be accepted at BSides. And I'm excited about it. I put my best effort into it, and I look forward to having a good session with you. So the topic here is browser fingerprinting. Before I go further, disclaimer. So I'm a data scientist at a financial institution. Nothing I say here represents my employer, what they may or may not be doing, their positions on any of this topic. This presentation is solely about method, things I've learned along the way, things I think can be beneficial to you. Now, another disclaimer here. This is a blue team talk. Some of you may be red team, some of you may be going back and forth. When it comes to browser fingerprinting, you may know ways of obfuscating, spoofing, otherwise messing with anybody trying to capture browser fingerprinting. I'm not here to debate that. I don't explore that. There may be other talks or other sessions where that's covered. So from a blue team perspective, what I'm interested in is how can we make use of browser fingerprint information for some use cases that are not usually discussed. Okay, so I'm not going to assume that anybody here knows anything about browser fingerprinting or the methods that I go through, so it's going to be pretty tutorial along the way. Those of you who are experts, bear with me. So when you hear the term browser fingerprint, think of all the information about a browser, and here browser means any device that engages in an HTTP transaction, any information that is discoverable from the server side about that client. So some of it comes across in the HTTP header. User agent string, accepted language, some other stuff. A lot more stuff and a lot more revealing stuff is available through JavaScript and other mechanisms that inquire into the user agent. Screen size, browser window size, browser plugins, fonts, session ID information, HTML5 canvas, and there's even ways of timing what the client is doing that can be sometimes folded into fingerprints. As far as I know, there is no standard definition of the entirety of what can be in a fingerprint. I believe from the literature I've seen that different people sort of focus in or limit the feature set to some things or other things. But it's potentially a very long list open to creative interpretations. Now, one of the key things about browser fingerprinting, how can this qualify as a fingerprint? Well, each one of these pieces of information carries information about how unique or conversely how generic a given browser is. And one way of measuring this using information theory is measuring the entropy in bits. So if all the browsers in the universe have one of two values for any given variable, then that would qualify as 1 bit of entropy. Okay, so the higher number of bits of entropy, the more information you get about a particular value. So plugins and fonts here on this list provide the most information. Whether cookies are enabled or not provides the least information. In general, browser fingerprinting combines information across all of these. So the challenge of fingerprinting, if you're going to do anything with it, is how do we combine all these different signals into a common signal we can do something with? So the most eye-opening academic work has to do with the HTML5 canvas. Below here, I don't know if you can read it, I've got some text from the article. The thing that jumped out is you write to the HTML5 canvas, you read it back, and you hash the result, and this makes dealing with the canvas fingerprints almost as easy as dealing with cookies from the server side. Okay? And this academic article says that this is 18 bits of information. And you can see that tops any of the other versions of it. I believe, I don't know, but I believe some approaches to fingerprinting only deal with things like the HTML5 canvas, where you can aim to get one signature to uniquely identify. Okay. If you've never had your browser fingerprinted, you can go to this site. This is a service offered by Electronic Frontier Foundation, and click the button that says Test Me, and it will give you a readout of your fingerprint and how distinguishable your browser is from every other browser that they've seen. So they've accumulated a database that they've applied this to, and I think this is an informative thing. I meant to have some screen captures here. If any of you use the Tor browser, you can go visit websites, and the Tor browser will give you a pop-up warning if that particular website is trying to fingerprint you. So I went to a couple of the popular sites. Go to the Facebook homepage. Even before you complete the login process, yes, you're being fingerprinted. You go to the Google homepage search box. No, you're not being fingerprinted. I have no judgment about that choice, what it means, what they're doing with it. It's just interesting to know. Okay, so now let's talk about the goal of this exercise for the purposes of this talk for people who are in blue teams. The most famous, infamous, well-publicized use of browser fingerprinting is to associate a particular session activity with a particular device for validation, fraud prevention, surveillance, lots of other things. I pulled this block diagram. It may give you an idea somewhat of what's going on the client and the server side. The key thing here is if you look at the line from the circle that says fingerprints in the database, they're not really doing much more than capturing fingerprints and storing them away, and they're going to look them up later to see, have we seen this fingerprint before? Right? Now, if this is associated with a login activity, you might say, I'm seeing a fingerprint associated with this login. Does that match any of the fingerprints I've seen before with this account? Right? So it might be part of some access authorization process. But this does not get at the core use case that was driving our need. So what we needed was general purpose fingerprinting, where we could do all the fingerprinting ahead of time and then answer questions related to fraud detection, prevention, response, maybe even marketing type applications, where we would want to know, are we seeing any browsers roughly like the browsers we're seeing here anytime in the past? So the key question is, we need a space of browser fingerprints with some kind of distance metric that we can use in our models that says, give me only the browsers that are somewhat close to this. Or give me the browser, show me all the browser signatures or fingerprints that are close over the last 2 or 3 or 5 years, because I may want to track the trajectory of given users as they upgrade their system. Now, a key thing, many of you know this, but as you use your system, as you upgrade your software, you will acquire different signatures. Your user agent string will change somewhat a little bit, or on major revisions maybe a lot. You're going to be acquiring fonts. You may be shedding fonts if you do it on purpose. Likewise with plugins. So even for an existing user, for an existing device, if I have an existing device, a lot of the things that fall into this fingerprint category are not actually fixed in time. So you want to understand how they might change over time. Let me say one other thing. So this became important in the context of fraud investigation because the question arose is, in the fraudulent activity, are we seeing use of toolkits that are being used in other places? Is there a connection between recon activity and actual exploit activity? So really trying to get a much broader sense of over the life cycle of exploitation, maybe as multiple threat actors might be involved, who might share common tools, can we see commonality among them? So as far as I can tell, and having read the literature, could not find any tool or method to solve that problem, which is why we went down this path. So my day job is a data scientist, and I told my boss, it's a challenging problem and it requires real data science thinking. He was excited to hear that rather than just some Hive queries and whatnot that we usually do. Quick show of hands, how many people consider themselves data scientists? How many people actually have done machine learning and Kaggle contests or anything else, feel comfortable knowing about machine learning? So the folks who raised their hands, for everybody else, I'm going to share something with you. This aspect of machine learning or data science is about feature engineering. It's about what goes into the models. In what I'm talking about today, I'm not going to be talking about machine learning, modeling, training, hyperparameter tuning, all that stuff. This is all the thinking that goes up in front of it. Now, one of the big trends recently, it's associated with this word called deep learning, is we're not, as data scientists, going to think about what we feed into it. We're going to feed in whatever we can find, and we're going to have the algorithm sort out what the features are. Now, some of you may be aware that Google Translate went through a big generational change 3-4 years ago. So prior to that, they had a bunch of machine learning models that had built into them things that were trying to recognize parts of speech and other grammatical concepts. And they shifted to technology related to what's called word to vec, which is word to vector, which is a deep learning technique which says, no, we're not going to provide any of that information at all. The algorithm is going to figure that out. We're going to throw tons of data at it, and the algorithm is going to figure it out. So it may be tempting. In fact, I'm going to show you some preliminary work here today where you treat this as the same. The approach I'm recommending takes a different angle. So hopefully that makes some difference. So in fact, I want to contrast 3 different approaches you might take. Most of us in the room who have familiarity with Unix tools, we have familiarity with tools that evaluate text files and how different or similar they are and highlight the changes. The first method is really closely tied to that, the string edit distance. So if you took the fingerprint, you just concatenated it all together, called that a string, and then did edit distance, maybe that helps solve the problem. Second method, similarly, you're creating giant strings out of the structured data, but you're going to apply some deep learning methods, in fact, the word-to-vec method. See what happens there. So the third method does not take that approach. It says, we're going to keep this structured information structured, we're going to apply domain knowledge in the encoding, and then once we're done with the encoding, we're going to concatenate the results. And I want you, at the end of this presentation, I want you all walking out thinking the words, muttering the words to yourself, sparse distributed representations. Sparse distributed representations. Is Alex Pinto in the house by any chance? Okay, so some of you may know Alex Pinto is one of the more well-known, well-regarded machine learning information security guys. His company just got acquired by somebody, so he's in a good place. Little is known about the underlying technology. I have reason to believe that steampunk deep learning is the core of his technology, but I can't verify this photo. So the deep learning method, again, you're offloading to the algorithm the task of featureizing, making sense of this. And conceptually, that approach is valid because if you have a Hadoop store and you have all your HTTP traffic over years and years, you've got no shortage of data. So maybe this approach works. So the sparse distributed representation, I'm going to talk about the benefits first because I spent a lot of my career in management and marketing. And then I'm going to talk about the technical part and close off with a little bit of implementation, a little bit of results. So the key thing about sparse distributed representations as opposed to condensed representations, right? If you have 5 different browser types, you might have encode that densely in a bit string of 3 or 4 bits, and every category has a unique bit string. Sparse distributed representations spread that out over 50 or 100 bits. And the advantage of it is it's much easier to combine features with different domains and granularity. You can do very easy partial matching, fuzzy matching, Boolean operations, even fuzzy Boolean operations, without descending into regex. So not germane to this application, but sparse distributed representations are very robust to noise, erroneous and missing data. A couple of other things, sub-bullets here I have listed that apply if you're plugging this into a machine learning model. But everything I'm going to talk about today is what you do that's short of that, and if you don't use machine learning at all. And the key thing for me here is the last major bullet is you can do this manually. Meaning I, as a programmer, I've taken, there's a company called Numenta based here in Mountain View. They have a system called hierarchical temporal memory. Their front end to this are sparse distributed representation encoders. So I've taken their encoders and applied them to this exercise, and it didn't require any fancy expertise from anybody. So that was a real advantage. The other big advantage for me was if you use method number 2, you have to keep retraining your encoder all the time. You may put 5 years of data into it, but you're going to have to keep retraining that month after month as new fingerprints show up. Because whatever encoding, whatever vector space that has been created will age and not necessarily gracefully. So the method I'm describing, you do have to keep upgrading it as new signatures come in, but it's not a machine learning retraining exercise. So it has dramatically different consequences on the resources and the skill set you need to do it. Okay, now we're getting down to brass tacks. What the hell is a sparse distributed representation? I'm going to walk you through step by step so you can understand the basic concepts. And after you understand this slide, you'll understand, I hope, a wide range of encodings that follow the same patterns. Okay, so the inputs here are a series of integers. These could also be floating point numbers, but the point is they're just scalar numbers. The output, when you specify the encoder, you specify the total number of bits that you're going to encode, the number of on bits within that total set, and the encoding is where in that total set you put those on bits. Okay, so by convention, the first element is encoded in the first, this case, 10 bits. The second element here is encoded in just shifting everything over to the right one, and so on. Now, the important thing for sparse distributed encodings is the overlap. Because the overlap determines either a full match or a partial match or any other sense of how close or distance these things are. So in the blue area, so these are all of the encodings that have at least one bit matching the first one, 0. So the key idea in sparse distributed representations is you're encoding your distance metric and you're encoding your rules or capabilities for partial matching in the encoding itself, which really takes a lot of work off of your logic and your systems that come later. Now, another feature of it is you can feed the system, the encoder, it's able to decode or produce matches to bit strings that do not conform to the encoding structure. So at the bottom here, I have a bit string labeled F that has 2 on bits. And if you perform a matching operation and you're counting any matches greater than 0, this will match all the inputs between 0 and 20. So in the same sparse distributed representation, you could represent all the numbers between 0 and 11, any subset you choose, and you also get a sense of how distinct you want these to be. If I'm looking for a 0, do I want to sometimes return a 1 if that's a fuzzy match? Now, there's a couple key variations here. One key feature of a sparse distributed representation is you can come up with what are called periodic encodings. So think of days of the week. Sunday is just as close to Monday as Monday is to Tuesday, and so on. So even if you number the days of the week 1 through 7, you want to come up with a distance metric or similarity that wraps around. So the way you do that here is you simply shift the bits so there's an overlap between the last element and the first element. Let's see, one other item here. So the other key building block here is how do you encode categories? Well, the way you encode categories is the same as here, but you don't have any overlap, or you have some predefined overlap if you want to have commonality between categories. But let's say you have disjoint categories. You simply use the same mechanism here. You just define it so that there's no overlap between the bit strings. And everything I'm describing here and waving my hands around happens in the code that sets up the encoder to the first place. And once you run it, you never have to revisit these things again. It just works. So there's 2 generic ways to store and manipulate these. One is the binary array. And for some purposes, especially if you're feeding machine learning, that's the way to go. For a lot of what I do, I store it as integer lists of the ones. Therefore, the size of my SDR is only, it's the length of how many on bits that I have. So I might have 1,000 bits or 100,000 bits. If I have a bunch of those that are empty, they don't take up any storage space. And when I'm looking for overlap, all I'm doing is matching integers. Do I have the value of 11 in both of them, for example? So these are kind of interesting when you look at them individually, but they're really powerful and really useful for this application if you look at them together. Here I've got 3 different types. Maybe they have 3 different configuration parameters. I can combine them into a composite encoder that takes a structured input. The structured input basically maps the first value in the structure to the scalar encoder, the second value to the categorical encoder, the third into the periodic encoder. And I can inquire that composite encoder for a similarity or distance value just as I would the basic one. So you get a richer distance metric without increased complexity in the programming interface and the semantics of it. So here's an example. Handling version numbers. I don't know if any of you have had experience trying to encode version numbers into a metric space, but version numbers, it's 1.5.0.3, and some of them have text thrown in. Unless you treat these as edit distances, it immediately gets to be complex. Maybe you punt on all the differences and you just look at the major revisions. But in a lot of cases, you might find important signal in how often a given set of browsers move through their minor revisions. You might find some patterns there. So I don't really want to throw that information away. So the approach here is you build a composite encoder focused, you basically parse the browser version number and you feed it into different types of encoders that handle each piece, and then you composite them together. So I want to share with you some results. These are work in progress, so this is preliminary. I'll be posting the work as I go on a GitHub site, available for use. The encoder software I'm developing will be open source, so you can use this. If any of you work in a Hadoop environment, you can use this Python software in your MapReduce code, so it should be pretty usable. So what I'm testing is I'm focusing on just the user agent string as my test case and doing these 3 different approaches. And the sub-bullets here show the pipeline of work. In case you haven't seen it, here's a sample of the browser strings. There's companies that do parsing of this and will feed you the parsed results. For this exercise, I chose to write my own little parser that pulls out some key information. Agent, the agent version, operating system version, device. If you look at some of these strings, there's version numbers all over the place. So it takes a fair bit of parsing skill to figure out which version number you're going to pick up depending upon what some of the other parameters are. So here's an example of that compositing that I was talking about before. I have different types of encoders for different pieces of this. Okay, so here's the kind of results I'm getting and the ways I'm evaluating it. So as a data scientist, the first thing I always do is I eyeball the results before I do any tests, before I do any fancy stuff. So here I've created distance matrix, so n by n distance matrix, and then I run it through multidimensional scaling with 3 dimensions, and then I visualize it. So what I'm looking for here is, I don't know if you can read the text at the bottom. These are color-coded Mac, Android, Linux, Windows, other. String edit distance, not everything is clustered in the same place. Maybe that's good, maybe that's bad. I see a bunch of very tight clusters. That could be significant. Now, if I compare that against the doc to vec approach, that gives me much more diffuse clusters. This could be more useful information if I'm trying to discern certain types of changes. Now, I apologize in advance. When I give presentations, I don't tease the audience. I meant to have this part done for this presentation, was working yesterday and today to do that. It's really work in progress. So I'm going to have similar visualization for the SDR encoding. And the key result, the payoff, is I want to track trajectories of actual individual user devices. And the test case here is I should be able to show that the SDR encoding does a better job of discerning evolution of single devices than the other two approaches. Here is a test case using a much smaller data set. This company, Udger, provides a service for parsing browser strings, user agent strings. Go to their website. I pulled the data from them, but they've done all the hard work to figure out how to parse user agent strings. But with just 115 data points, rather than looking at all the fuzzy clusters, you start to see how scattered these things are in space. And if you really care about fine-grained distances, it's not enough to have just everything show up in one blob. And it's also not very comforting to have these things spread out all over the case where you may be losing information about their relationships. So last thing I want to share with you, since this is the last day of B-Sides, is my nomination for the coolest creatures in InfoSec. The capybara, which is from Brazil. I noticed the goat standing on the head over here. That is a pretty cool creature, and the monkeys that are doing the cleaning of it. And I mentioned Alex Pinto before. Alex is also from Brazil. So I often associate Alex and his personality with the capybara. So here's your key takeaway. Sparse, distributed representations. The key is they encode similarity. Similarity is not computed afterward. You can derive it by different ways. One key thing is really important. You can do weighting and filtering. If you have 20 or 40 or 80 encoders, if you filter some of those out, you're basically enhancing or removing some of those factors in your distance calculation, and that's really the key to some of the applications we're working on. Nothing I described here requires machine learning. It doesn't even require a data science background. I'm going to be releasing the Python code and some of the R code for visualization. Capybaras are cool. So is Alex Pinto, because they're from Brazil. So, it's the end of my presentation. Any questions, comments? Can't see everybody's hand. Anything, anyone? All right, so for my benefit, because maybe I'll see feedback forms later. Show of hands, how many people think what they heard today was surprisingly valuable? Okay. How many people think today's talk was a waste of your time and you're only happy to be here because of the comfy chair? All right, I appreciate that. So everybody else is in between? That's cool. All right. So thank you all very much for your time. I'm available afterwards for a few minutes. I may even see you up in the happy hour.